All right, guys, we left off with density as mass divided by volume. Our units for convenience were solids, liquids, and gases. For solids, we used uh, grams per centimeters cubed. Centimeters cubed was our volume. Or for liquid, we use grams per milliliter. And for gases, we use grams per liter. Moving on from that, we want to talk about another physical property, states of matter. States of matter are an important physical property, deals with solids, liquids, and gases. Now, I want to approach this from a point of view of energy, meaning in a solid, you have a definite shape and volume, it's almost incompressible, but you have the least amount of energy. So, in terms of energy, there's the least amount of particles colliding and lowest temperature. Liquids have some energy. Liquids can move around, they can flow, they can splash, but they do have a definite volume. Your can of Coke could be 12 ounces and you pour it into a cup. It's still 12 ounces, even though it takes the shape of the container. These are almost incompressible and they expand slightly when heated. So liquids have some energy, solids have the least energy, gases have the most energy. They're doing the most. It takes the shape, it takes the volume of the container as well. Vapor is another word that we use to describe the gaseous state of a substance. And I want to model this using particles on an online simulator. So check out these particles here. It is telling me this is neon. Now we normally have neon as a gas. As a gas, the particles of neon would be bouncing around and having many collisions. Temperature wise, it's high at 56 Kelvin. So that means it has the most energy. As a liquid, it's together. Some particles seem to want to escape, but liquids, as we know, can slosh around, but generally they stay together and they take the shape of the container. So the volume of this liquid isn't changing. The gas volume, that's going to change whatever my container is, that's what the volume is going to be. This liquid, though, seems to stay together and have the same volume. Uh, the temperature or the amount of energy affects the collisions. There's a lower amount of energy, it's 28 Kelvin, so there's less collisions. The solids, there are some collisions. There's a wiggle and jiggle effect going on. But my temperature is the lowest of the three, it's 14 degrees Kelvin. If I were to add heat to this, you would expect it to take on the properties of a liquid. So we're going to add some heat and they start to collide. There are more collisions, more energy, more collisions, and the particles are moving around now. Now they're taking on properties of more like a gas. Let's turn up the heat. So the more energy or the more heat energy I add, the more collisions, and it changes the state of matter. Okay. Let me reset that, and I'll look at another particle, argon gas. Let's start out with solid argon. What happens as we increase the heat? Give it more energy, you get more collisions, and it becomes more like a liquid. If I continue to increase the heat, it becomes more like a gas. What if I were to take away the energy? If I take away the energy, there's less collisions. The gas condenses, becomes like a liquid, and it condenses so much with less and less energy that it just becomes a solid where the particles are sort of together as close as they can be and jiggling and wiggling even though it's a solid. Nothing has like 0 Kelvin energy. That's why. There's nothing that is absolutely zero. So there's always going to be some kind of movement, some kind of wiggle jiggle. Right. Okay, physical change, we're going to cover real quick, and we're going to cover mixtures. So we talked about uh, physical properties. During a physical change, I want you to know that the properties of the material could change, but what it's made of or the composition, it does not. So in a melting ice cube, it's still made out of water. All right. If I put water in my freezer in the ice cube tray and it turns to solid ice, it's still made out of the same particles. So the composition didn't change in that case. And that kind of thing can be reversible. So another thing with physical changes that could be reversible, some physical changes are not. Okay. If you cut your hair or crack an egg, you can't undo it. You can't uncrack an egg. But the main difference between physical change and, say, chemical change is that the substance or the composition of the substance does not change. With that said, we're going to get into mixtures, we're going to get into compounds, we're going to get into elements. First, let me hit on mixture. It's a physical blend. It's two or more components. So I like to think of like alphabet soup. You can pick apart the different letters out of your alphabet soup, and even something like chicken noodle soup. You can pick apart the noodles, you can pick apart the chicken, the little corn, and the little celery and carrot. So in a soup, they're not made out of the same uniform substance. So that would be heterogeneous. Heterogeneous mixtures are examples like soup or alphabet soup or cereal and milk, where it's mixed together, but it's not the same substance. Pizza, believe it or not, is a good example of a heterogeneous mixture. If I take off the pepperoni on top, I have cheese underneath. What's under the cheese? Well, there's sauce, and the sauce is on top of dough. So it's one pizza as a mixture, but it's all made of different parts. A homogeneous means it's the same parts. The composition is uniform, all the same. Another word for this would be solution. Like you can make iced tea out of a solution, or Kool-Aid, or salt water. Homogeneous mixtures are solutions. Now, a lot of those are liquids. There are even some gases. The air that we breathe is homogeneous. Okay, it's uniform as far as we can tell, but it is made out of other substances than just oxygen. For example, there's a lot of nitrogen in the air that you breathe. Some of the solids, like the steel cube that we looked at on the density cube set, that's a mixture of iron. It could be mixed with chromium and nickel and even carbon. So some solids even make up homogeneous mixtures. How do you separate these things? Well, you're going to use the different physical properties to separate them. Salad dressing, oil and vinegar is great salad dressing. But if you really had to separate it, you could decant that mixture. And what that would do is you would put it in a special bottle that helps the substances separate. Another way you could do is you could freeze the olive oil and the vinegar mixture. And the olive oil is going to freeze before the vinegar, so that's going to turn solid first. Another way to separate mixtures is filtration. Think of like coffee filters. When you make coffee in the coffee pot, you put the coffee filter and the liquid goes over it, and the solids do not pass through. They're filtered. Distillation is the last method that I want to talk about. In distillation, the liquid is boiled. It produces a gas or a vapor, and that is condensed back into a liquid. Now, I'm going to stop there and give you some time to work on your assignment. So have a great day. We'll see you tomorrow. Bye.